So this is the paper with Will Troiani, who I assume is here somewhere, building on a bunch of work over many years, which I'll come to a bit later. But I want to start way back, even before I came to Melbourne. So this is a paper, I don't know why it says 2024. This is a paper from 2008, and it hasn't been updated on the archive, so I don't know why it's got this date. But anyway, so when I was a young postdoc, I did a PhD in algebraic geometry. I went to Bonn, to the Hausdorff Center there to work with Daniel Hoybrechts, who was an algebraic geometer. And the first thing he gave me when I arrived was this paper. They were running a seminar on it, and I sat down and tried to read this. A very, very difficult paper. What has it got to do with anything in this talk? Well, this is the paper. I got an idea from this paper, which has stuck with me for many years. And I want to tell you the idea because it's basically the most important idea you need to understand in order to sort of grok where we're coming from when we talk about this idea of programs as singularities. Okay, so now let's talk about A infinity categories. Well, not really. So I've highlighted a few things here. We claim that the set of isomorphism classes of objects of category C can be blah, blah, blah in constructible sets. This gives a closed scheme. This is sort of like some idea of taking a category which you think of as a discrete object with kind of objects like vector spaces and linear transformations, say, turning that into a space itself. So having this kind of set of mathematical objects itself a space, like having a topology where objects can be close to each other and you can talk about geometry of that space and so on. And even more than that, setting up a situation where objects, mathematical objects, are critical points of some function, which is called the potential in this language. So it doesn't really matter what the setting of this is. It doesn't really matter what the objects involved are. But I want to put in front of you this idea, which has been very successful and very useful in various other parts of mathematics, that if you have a set of mathematical objects, it might be useful to imagine a setting in which those objects, which maybe are discrete, sit in a larger space of continuous objects, such that the original discrete objects you're interested in are critical points, that is, like minima, for instance, of some function on that larger space. And the reason that might be interesting is because you might be able to realize the kind of internal structure of your mathematical objects as geometry of that potential function. And in this particular case, that is kind of all this stuff on the page is about doing that. It's about actually having this function whose critical points in the mathematical objects have geometry that's actually relevant to kind of what's inside the object. And I'd never seen this idea before. It's not new to Kontsevich and Soberman, but I'd never seen this idea before going to Bonn, and this had a big impact on me, even though in some sense I failed to understand this paper. Okay, so just to repeat that idea, it doesn't matter if you don't know what categories are. It's not really the point. Just imagine these circles as mathematical objects of some kind, which are maybe built up out of pieces in some way. And in a category, you have arrows. You can compose arrows. So there's an object. And so what I'm asking you to imagine is some kind of function on this plane, which is where the objects of my categories of my category live, which has as critical points, for example, global minima, these objects. Well, for that to make sense, you actually need to be able to define the value of this hypothetical function, like away from your objects, right? So either your objects need to be continuously parameterized in some way, or you need to invent a larger space in which your objects live, maybe like almost objects, let's say, such that your potential function is defined for those and your original objects are selected in, like picked out in some way among those almost objects by some condition, for example, being a critical point. Um, okay. Now, in the setting I was just describing, well, not really, but the Kontsevich-Silverman paper, like there's something called A infinity modules, there's solutions of some equations, and you can look at things that don't quite satisfy those equations, and those are the almost objects. But depending on your setting, you might have to cook up the almost objects in some other way. Now, suppose that you did that somehow. So you've got your mathematical objects, you've got this space of almost objects in which they sit, you've got some function that assigns some value to those almost objects, and you're interested in the points where that potential is minimized, and those are like include the objects you were originally interested in. What would it mean to have some way to vary along that set of minima? That would kind of have to be like a way of varying a mathematical object, right? But there are often ways in which mathematical objects can be varied, especially when they have parts. So if you have a mathematical object with three parts, like this funny thing here, built up out of three pieces, well, there's sort of like a natural set of ways you could vary that object, which is like dial up the sizes and move bits around. Now, you wouldn't move the cone to another face. That would be kind of like a discrete jump, like a change that would not be continuous. But you can imagine there's all sorts of continuous manipulations you could do to your object. And depending on your setting, that could be, for example, changing the weights in a neural network without changing the function. That's the example I'm trying to get you to think of here. It could be changing a Turing machine in some way that we'll talk about later. It could be changing something about the way you construct a representation in representation theory, etc. Okay, but you see here something, in this picture, the geometry of this surface, like this kind of sine function at the bottom of the potential well, its geometry, like the fact that it's one-dimensional here, is related to the fact that there is like some particular ways you can change the structure of the object that is parameterized by that line. And that's sort of a paradigmatic example of how the geometry of this potential function is related to how the objects that it parameterizes are built up. And so this is how internal structure and geometry are often related in these kinds of situations. Okay, so that's all very abstract, but I wanted to paint this picture before I got into the details. So this is a kind of motivating set of ideas for me getting into this kind of story many, many years ago. Then you can ask a kind of odd question, right? So, well, if you can do this kind of thing for coherent sheaves on Calabi-Yau threefolds, which is what Kontsevich and Silverman were doing, well, maybe you could do it for proofs or programs. Those are mathematical objects too. So here's like some slightly crazy questions, right? So what potential are programs a critical point of? Question 2, is internal structure of programs reflected in geometric structure? So just to reiterate, those two questions can be made sense of and have positive, very deep and interesting answers in other parts of mathematics. But okay, can we do that for programs? And then I had some sort of harebrained idea how to do that. This was like 10 years ago. Never really quite succeeded at that, or didn't succeed yet, maybe I should say. But anyway, this was on my mind and I was trying to do this. You might ask, why? There isn't a reason. It's just kind of seems like a fun thing to do and nobody could stop me. So I tried to do it. More seriously, you could say, well, if you want to understand the nature of computation, maybe you could try and model it in geometry. And that was sort of the motivation for that. Okay, let me fast forward a bit now to a series of papers. I'm not going to talk too much about Erhard and Regnier's work, but it's really important also as a source of ideas for all of this. And so I want to flag that at the beginning. I'll probably mention it one more time as we go along, but it's sort of deeply ingrained in this perspective as well. So a series of papers of myself with James Cliff, James Walbridge, former master student Tom Waring, and most recently with Will and Billy, who's going to show us some pictures at the end of this talk, has been examining various aspects of this kind of idea. Like, can we find a way of putting discrete programs in a continuous space and realizing them as critical points of an analytic function in a way that's interesting? So that would look like the following. It would look like programs. Those are the circles sitting in some continuous space. That's the square, where the rest of the square, I mean, really those programs should be on the vertices of the space. The rest of that square has to be something like an almost program, whatever that means, like something that's not quite a program, in such a way that there's a potential over the full space with the true programs as critical points, and the geometry of that potential at the programs being interesting. Okay, so to restate that more precisely, we want to embed programs, say pi. I'm not saying what language, and in fact, I kind of also just mean intuitionistic proofs. Embed programs into a continuous space, we'll call that W, with some function on it, H, such that the program's a critical point of H. And just to say what that means that all the partial derivatives of H at pi are 0. That's Desiderata 1. Desiderata 2, or B, is that should actually be interesting. So the geometry of, so germ just means take a function together with a point. So the geometry of the function at that point should reflect something about the structure of the program. It's not hard to do A. So there's many ways of taking, say, continuous relaxations of Turing machines, and like continuous Turing machines or analog Turing machines. There's many ways of doing it. The thing that's actually non-trivial is B, like actually having the geometry of the germ reflect the structure of the program. And so what we did in this paper, well, what we've done in a series of papers culminating in this work, Programs of Singularities, is to start sketching out a approach to doing that where B seems to be satisfied. It's kind of vacuously satisfied if you just decide that structure, like there's no such thing as structure of pi, then there's nothing to reflect. So you have to make some decision about what structure means. A motivation for the way we did this is that you can, if you think of pi as an intuitionistic proof under a kind of Curry-Howard kind of correspondence, then proofs have structure from denotational semantics, and so you can use those kinds of techniques to come up with a way of doing B. I'm not going to say much about linear logic or denotational semantics. That's sort of how we came to the thing we do. It's not necessary to understand what ended up in the paper, but it's definitely the way we think about it. And so kind of required to really follow at least the way we present it there. So maybe the main reason that it's like worth following the kind of logical ideas behind this project is that it, from this point of view, it's like not hard to see how you might do something like this. And to say very broadly why, if you've constructed your program in some sort of, like, say, natural deduction or lambda calculus, where you've built it up from pieces, so a lambda term is built up by lambda abstractions and function application. So the program has a kind of tree structure. And so if you assign meaning to the pieces, you've assigned a meaning to the whole, and that's the kind of internal structure of the program. And if you can somehow assign to programs points in a vector space in a way that reflects that construction, then it's like that's a candidate for your almost programs, right? So if you can find denotational semantics of proof theory in vector spaces or manifolds or schemes or some other kind of continuous mathematical objects, then you kind of like automatically, instantly have a candidate for this kind of almost program, which is just take the things in the space where your denotations live, which are not the denotations of programs. And that's what we did. And so now I'm going to describe kind of, without invoking that origin via linear logic and denotational semantics, what the answer looks like. But I'll pause here for questions, maybe. Including kind of vague questions about the general sort of approach or idea or motivation. That's perfectly fine. I'm kind of, my main purpose in this talk, the paper has all the details, right? My main purpose in this talk is maybe to try and outline some of the thinking that goes into it and some of the, like, the reason why you would do this at all.
Would you mind just giving some more detail on what you mean by the geometry around that point?
Yep. So at a concrete level, you could just read this to mean the Taylor series expansion of h at pi. Or if you think about writing h in local coordinates at pi, for instance, the very first geometric question that you would ask is the Hessian of h an invertible matrix or not? And if it is invertible, then by geometry, you might mean what are the eigenvectors and eigenvalues of that matrix? If it isn't invertible, then you might ask what is the kernel? And then beyond that, you would start getting into actual algebraic geometry. So you'd be studying things like, it's a bit hard to describe in brief terms, but
yeah. So and the hope would be that there is some sort of maybe bijection between the structure of the program, and say you chose to do eigenvalues of the Hessian, then maybe there's a bijection between the structure of the program and the set of eigenvalues of the Hessian.
Bijection would be too strong a word, but yeah, like the hope is that many aspects of the structure of the program are reflected in these kinds of things about the geometry. Yeah, so we'll see an example at the end actually of exactly this with the Hessian.
Okay, thanks.
Other questions?
Yeah, just I'm really curious about this idea of embedding objects of a category as points in a continuous space. You said that you had never seen this idea before when you read that paper, so I'm guessing I probably have also not seen it. But there's like one example in my head that I wonder if it has anything to do with that, which is the idea that, for example, when you're doing geometry, you have this idea that you can take a smooth map between two spaces and view that as a linear map between coordinate algebras. Is that in any way related to this? Because in that sense, you would say that like my smooth maps, the things I'm interested in, they live in a larger space, and they are the elements of that space which satisfy a homomorphism condition. Is that anything like this theme, or?
Yeah, that's a good example actually. So that's a case where I mean the set of smooth maps between two manifolds is not itself a manifold because it's infinite dimensional, but you can make a space out of. So that's an example. I mean, I'm not sure I'm completely following, but it's not unusual for the set of transformations between two things to itself be a thing of the same kind. So if you have two vector spaces, the set of linear transformations is again a vector space. If you have two manifolds, the set of smooth maps is not a manifold, but under some conditions, it can be thought of as an infinite dimensional manifold. So that's a case where transformations between things become things of the same type. The case where you get so it's not that unusual for the objects of a category to themselves be something you can think of as a space, at least in some sense. So, for example, if you take, the example that appears here is coherent sheaves. So if you take a space and you take sheaves on the space, then often the sheaves can be varied continuously in a way. And so you can think about them, you can think about like coordinate functions on the space of these objects that live over the original space. And so then like you have continuous families of objects. So that's, or if you think about, so it's relatively common to have objects of a category naturally thought of as not just a discrete set, which it is in the definition, but itself like having additional structure. What is more sophisticated, and is what Koncevic and Silverman are doing, is kind of providing a sufficiently abstract language in which you can kind of manufacture that space in some suitable sense, even if it's not obvious how to do that from the way the category is constructed. Something like that.
Okay. What do you think is the simplest example you would point to of this phenomenon of objects becoming critical points of thinking? Is it this one in the paper, or is there a simpler example that is found somewhere?
Yeah, the one I was highlighting in the paper is, I mean, that was talking about infinity categories and so on, but if you look at the easiest example is representations of a quiver, I think. So if you take a set of representations of a quiver, that naturally can be thought of as like a space. And that's one of the key examples in this paper. So, I mean, a representation of a quiver is a very simple object. It's just a bunch of vector spaces and linear maps. And then you can, so it's actually it's basically the same reason why deep linear networks are a thing. So if you take a bunch of linear maps, then you can kind of reparameterize the linear maps by continuous changes. And so that means that your set of representations of your quiver sort of naturally is a space.
Okay, yeah, I think that makes sense.
Okay, thanks for the questions.
Sorry, I have a question too.
Yeah, go ahead.
So when it comes to embedding categories into geometry, do the morphisms get embedded too? And if so,
yeah, great question. Yeah, the morphism sets become vector bundles over the space of objects. So if you think about it, if the set of objects is a space, then what are the Hom sets? Well, I need to provide two objects, and then I get a vector space. So if my category is C, and I think of the set of objects as a space, then taking C cross C, and if I take a vector bundle over that, whose fiber over each point, which is a pair of objects, is the Hom set. And then you can formulate the rules of the categories in terms of morphisms between those vector bundles and so on. So yeah, that's pretty cool. Okay, I want to briefly remind you about Turing machines, because we're going to talk about universal Turing machines and then like kind of perturbing Turing machines in some way. So on the left here, you see the specification of a Turing machine. So a Turing machine has a set of symbols, in this case, sigma, that's blank, that's the box, AB, that's the alphabet that it recognizes on its tape. There's a set of states, and the way a Turing machine works is if you look down the bottom left there, so AB, by AB, I mean a tape, a one-dimensional tape, which is all blank to the left of the A, all blank to the right of the B, and has A in a tape square and B in the next tape square. So a Turing machine has its sort of head looking at a given square. In this case, if you look on the right, it's looking at A, and it's in state reject. So the reject is this kind of label above the arrow. It's meant to represent like an internal state of the Turing machine at some given time. And in that case, you look at the table and you see, okay, if sigma, which is how I refer to the current symbol that's being read, is A, and the current state, which is Q, is reject, then there's a row that starts with A, reject, and then you look up the triple A, accept, stay. And that tells you what to do. So you should write A. In that case, you don't do anything. You just rewrite A over the A that's already there. You should, however, change your state to accept, and you should stay. So that's the instruction for the head, that is the arrow. So it should stay where it is. Okay, that's not very interesting. Let's consider a string BA on the tape at the beginning, and you start in state reject. If you look over on the left-hand side, that's this row, B reject. So you should write B, you should stay in state reject, then you should move to the right. Now you look again, and if you see an A and you're in state reject, then you should change to state accept, and you should stay where you are. So you switch to accept, and you're done. Okay, so this is a specification of a machine that looks at an arbitrary string of A's and B's on the tape. And if it starts with its head over the first symbol, will, given enough steps, scan through the string and end up in state accept if and only if the string contains an A, hence the name detect A. And if you look at, I'll give you a moment to look at the tuples to verify that you believe that this is actually what it's going to do. Are there any questions? This is not the only Turing machine that computes this function, the function being, if you like, take as input a string of symbols in A's and B's, and as output accept or reject. Detect A is one Turing machine which implements the function that returns accept if and only if the input string contains it. Okay, what's a universal Turing machine? Well, I'm not going to tell you in general, but a particular universal Turing machine basically is able to act like any specification that looks like a table like this. So if you take that specification in the table and you sort of unravel it into a line and just plop it onto a tape. So you start with the first row, blank, reject, stay. And then you write the second row and so on until you've written all the tuples onto a tape. So you've put that specification or that code of that Turing machine onto the description tape. So the universal Turing machine, rather than having one tape with one head that moves around, has three tapes, and it's going to simulate the machine on its description tape by having another tape, the state tape, which contains the kind of representation of the state of the simulated machine, in this case, detect A, and it's got a work tape which contains the stuff that the simulated machine is operating on. And by changing what's on the description tape, you can make the universal Turing machine behave like any machine. As long as, I mean, there's some details here with the alphabets and so on that I'm going to elide, but that's the idea. Okay. So what am I trying to do here? I'm trying to introduce a way of constructing almost programs, right? So we're going to take discrete programs, we're going to sit them in a larger space that's continuous. How are we going to do that? Well, we're going to think of a program, first of all, as a code for a universal Turing machine. So that's some data on the description tape. And if you imagine the universal Turing machine simulating that code, so it starts with some input on the work tape, it's going to check the description tape to see what it should do in the first step, and then do it by manipulating the state and work tape, and then look again, compare the current state on the state tape and the work tape to the description tape, see which tuple it should execute, just in the same way we did on the previous slide, right? Like on the previous slide, we looked at the stuff on the right-hand side, then we consulted the table, and then we did a thing, then we consulted the table again, and we did that until we were done. So the UTM, Universal Turing Machine, will do the same thing. And that's a discrete dynamical system, discrete time and discrete sort of state, right? The state being all the stuff you see on this slide right now, the state of the UTM. So that's some trajectory through the possible states of the UTM. And that discrete dynamical system can be perturbed. And that perturbation is how we're going to think about almost programs or noisy Turing machines. Okay, so how are we going to perturb a program? Well, the program is the code, and here is the code, right? The table that has the current symbol under the head in the first column, the current state in the second column, and then what you're going to write, what you're going to change into as a state, and what direction to move. And the possible perturbations are to change the data in columns 3, 4, and 5. So just pick one of the rows. Let's take the row A, reject. So you see these numbers, 11, 12, 13, 14, 15. Okay, so 11 represents like the way you could change the behavior of the simulated machine in the case where you see an A on the work tape and are in state reject, to is instead of rewriting an A over the A that was already there, replacing it by a blank. Likewise, instead of that, you could replace it by a B. Or you could, and this is 13, you could, instead of accepting, you could reject. Obviously, that change is going to break the machine, right? However, if you think about it, I mean, you probably didn't have enough time with the description of the machine to immediately see this, but maybe I'll pause here and you can have a think. If I was to replace the A by a blank, rather than just rewriting an A over the old A, this is not going to change the input-output behavior of this machine. Because it's already accepted. And once it's accepted, look at the blanks rows. So blank reject, reject. Blank accept, accept. I mean, maybe it's a bit hard to, I'll just go back to this version. It's a bit easier to see. Sorry, if you look at the bottom right, suppose you're looking at a blank, then if you're in state reject, you stay in state reject. If you're a state accept, you stay in state accept. So if you've just like seen an A, you go to state accept, and then you write a blank over it, you're just going to stay there looking at the blank, contented and still accepting. Right? So having this change from
sorry,
11.
Maybe it's worth mentioning that by the output not changing, you mean the state. What's written on the tape does change.
Oh, thank you. Yeah, that's true. Yeah, thanks for that. So when I was describing earlier the input-output behavior of this machine, what I mean is the input is what's on the work tape to begin with, and the output is the state, like accept or reject. So this is like a language. The Turing machine's job is to classify the inputs.
Can I ask a question?
Yeah.
I thought that once it accepts it, oh, I see. I guess I was confused. I thought once it accepts, it just stays in the accept state by definition or something, but maybe this behavior is encoded in the program.
Yeah, thanks for the question. That's right. So the definition of a Turing machine, there's like subtle variants. So there is no halt here. So often a Turing machine comes with a specification of an initialization state and a halt state. And if you get to the halt state, then the convention is that you don't do anything anymore. So yeah, neither of the accept or reject states is treated as a halt here. And yeah, implicitly, I'm inviting you to think you run this for some number of steps, which I'm not specifying. But it's a little ambiguous. That's okay. So the idea here is that there are 30 ways to change the specification of this machine. Some of them don't actually affect the behavior. Okay. And in fact, all the ones in blue will not change the input-output behavior in the sense that I just described. Okay. So the idea, which I'll introduce a bit more formally in a moment, is that, so I'll give a fine version in a moment, but the coarse version is, imagine the universal Turing machine. It's this dynamical system simulating some other machine given by the code on its description tape. And so think about like the CPU of the UTM is like physically localized somewhere. And whenever it wants to figure out what is going on the description tape, it has to take a look. It has to receive a message. It has to interact with the description tape. In the same way that when you're trying to simulate this machine, you're looking at this table and you're reading the rows. And suppose like your eye scanned incorrectly, and instead of reading to the right in a given row, you read from the row below, right? So there's like some error in your processing of looking at the description tape. Okay, so whatever that model of noise is, if every time the UTM is looking at the description tape, it has some possibility of making one of these 30 mistakes, that's going to change the trajectory of the simulation. Okay. So it's by allowing errors of some kind that we're going to introduce the deviation from the normal Turing machine code. The actual way in which the errors are propagated is more similar to every square on every UTM tape. So on the work tape and also on the state tape, it's like every square being a different noisy channel that allows you to sample from some distribution that lives on that square, and which ultimately is derived from stochasticity that's on the description tape. I'll try and be a bit more precise about that in a minute, but it's difficult to do that in a short period of time. Okay, so here's what a noisy Turing machine is then formally. Maybe it's easier to just say what W code, that's an ordinary Turing machine code is. So these are only Turing machine codes with a given set of symbols and states. I can say more about that at the end, but I maybe will not do it right now. So to specify a normal Turing machine code, you have to say for every possible symbol and state, what to write, what state to transition to, and what direction to move. So that's an element of this Cartesian product. A noisy Turing machine is going to give some distribution over symbols to write. So the delta here means probability distributions. It's going to, given a symbol that's being read and a state, give some distribution over symbols to write, a distribution over states to transition to, and a distribution over directions to move. And we say noisy because we think of that distribution as being an error channel. So that tells you the errors that are possible when you are trying to read from that square on the description tape, you being, well, the UTM, like the thing that is attempting to simulate the machine. Okay, I need some notation for the next slide. So curly U is the UTM. So it has the description tape, a state tape, and a work tape. If you put X, some sequence, I should have said somewhere, but X is in sigma star. So X is a sequence of symbols in the alphabet. If you run the UTM with X on the work tape, and to start with, let's say some actual Turing machine code on the description tapes, this is normal simulation. Run it for T steps. T is fixed in this story. Then after T steps, there's something on the state tape, and we call that UW star X. Now, if you perturb that actual Turing machine code, notice that W code is a subset of W, right? It's the points of the vertices of some hypercube. If you perturb away from W star to W, so that's an actual noisy Turing machine, then you following some protocol for how to actually sample from those error distributions at appropriate times. So now you've got some probability of getting errors when you read the description tape, and you need some way of describing how those errors propagate. Given some way of doing that, if you run that noisy Turing machine for T steps as well on the same input, you get now not necessarily a state on the state tape, but a distribution over states. And that will be close to what you had when you, I mean, if W star is close to W, that'll be close to UW star. Okay, I still haven't told you exactly how the errors should be propagated, but are there any questions about this slide? Okay. Yeah, I'm not actually sure this helps too much. Yeah, I think I'm going to save questions about exactly how this propagation error works until the end. So I think what I've said so far is sufficient for a first pass, but I might come back to this if people ask questions about that. Okay. So remember, the original motivation was to take programs, construct a space of almost programs, put a potential function on that space of almost programs, and then do something with critical points. So we've now constructed the space of almost programs. That's W. Right? Almost programs are noisy Turing machines. Real programs are Turing machines. Okay. So now I'm going to explain how to put a potential function on that space. The potential function depends on additional information. The additional information is y. So y here is a function of x. So it is, for example, in the detect A case, the function that maps a sequence of A's and B's to accept or reject. As I mentioned, there are many Turing machines which have that input-output behavior, for some definition of many. Okay. Classical program synthesis just refers to, given input-output behavior or some other set of constraints, produce a Turing machine with that property. And we can measure the deviation of a Turing machine or a noisy Turing machine from having that property by, for example, taking the KL divergence from Yx is just the Dirac distribution to the distribution that is output by this simulation protocol for the noisy Turing machine after t steps. If you do that KL divergence, so take the expectation of the input distribution of the KL divergence of that output distribution to the correct one, you get some function of W, which turns out to be, perturbing things a little bit, turns out to have the same asymptotic behavior as this expression that I'm writing down at the bottom. So the expectation of X of the probability of U. So take a noisy Turing machine, simulate it for T steps on input X. Take the probability that that is wrong. So if there's only two possible states, like accept and reject, for instance, in the detect A case, then when you run the universal Turing machine on input WX, it's some distribution over accept and reject. Take the probability of the wrong answer. So that's the probability that y of x is not equal to uwx. Square it and take sum over x qx times that. So this is our potential function. This is going to be 0 if and only if this noisy Turing machine gets all the answers correct. Right? It actually puts probability 1 on all the inputs which are supposed to be sent to accept and reject it otherwise. Okay. So let me state theorem. So on the top left, you see a sort of diagram of the idea here. The sort of, you see this two simplex, this triangle in the bottom left with a vertex marked M. So that is an actual Turing machine. So a Turing machine code sitting in the larger space of noisy Turing machines, which is this triangle. And when the universal Turing machine is going to look at that code, maybe I'll skip this read error line. Let me think for a moment how I want to say this. All right, so I want to justify the claim that the geometry of H, which is defined on all noisy Turing machines, at an actual Turing machine. So an actual Turing machine sits in this broader space. First of all, it is a critical point of H. And secondly, I want to argue that the geometry of this function H near that point reflects something about the internal structure of the Turing machine. And so this theorem is meant to be the kind of bridge to doing that. So if we look at the Taylor series expansion of H at a Turing machine, in this case M, the coefficients in the Taylor series expansion, so the W's are some coordinates in the probability simplex that represent varying the code in some particular way. For example, those 30 directions which I showed you are the 30 local coordinates at the detect A point in the space of noisy Turing machines. And if you compute a Taylor series coefficient of H, it's some combinatorial object, so it's a sum over tuples of integers, and the important thing here is the thing inside the brackets. That's the expectation over the distribution of input strings of a product of two random variables. The random variables are counts of error syndromes. And the error syndromes are ways of having the, so if you think about a universal Turing machine, which is reading from the description tape and sometimes has errors, then a given run is described deterministically by which errors actually occurred. So you have just this large set of error syndromes, an error syndrome meaning a particular series of reads, some of which were correct and some of which were incorrect. And so ASX is the number of such error syndromes, of possible runs of the UTM on the input X, which have errors of a certain weight. I won't go into what weight means. Errors of a certain weight. And those errors in reading from the description tape when trying to execute the machine actually caused an error. That is UXY, UX gamma rather, which represents what the UTM does on input X if it actually sees read errors from the description tape of the prescribed form by this gamma, this error syndrome. Does the output of doing that simulation with those particular errors actually change the output of the simulated machine from what it was before? So that is M of X. So M of X here denotes the state at the end of the T steps when M is executed on input X. Okay, so so you've got the UTM, it's like without any errors, it just runs the Turing machine that is described on the description tape and gets M of X. If you run it with error channels specified for the description tape, it's running the simulated machine, and every now and then it goes to look at the description tape and it actually doesn't get the right thing. It's actually more complicated than that, but this is sort of the first level of trying to understand what's going on. So, okay, it actually had some errors reading from the description tape, but some of those errors maybe don't matter, right? So we talked earlier about in detect A, if you happen to write over an A with a blank, that would be doing the wrong thing. That's not actually what detect A0 says to do. But suppose when you went to look at the description of detect A, you inadvertently executed that rather than what the detect A table said to do. That wouldn't matter. You wouldn't actually have flipped the output of the algorithm to reject rather than accept, or vice versa. So that would be an error in reading from the description, which doesn't matter. And you don't count those. So ASX is the count of those error syndromes which actually matter, which actually flip the output. Here I'm assuming M is actually a solution. Sorry, I should have said that. So in this slide, the Turing machine M is a solution to the synthesis problem. It actually computes the function Y. And so we're talking about errors in reading from the description tape, which cause the simulation to deviate from M, which already has the correct behavior. Okay, so the Taylor series expansion of H is sensitive to the correlation of these two random variables, which are talking about errors in reads from the description tape, which actually flip the output. Okay, so the upshot here is that internal structure in the Turing machine translates to patterns in these correlations of ASX and ATX. I'll say more about that in a moment, but you can think about it this way: the way in which certain tuples in the description of the Turing machine interact with each other means that errors in reading one tuple may or may not compound with errors that occur in reading other tuples. And if two tuples often work very closely together to produce an output on a given part of the input distribution, for instance, then the effect of errors in reading from those tuples when trying to simulate the machine will be quite correlated. Whereas if two tuples are, for example, only ever used on distinct subsets of the input distribution, so some part of the description of the machine is used for some inputs and other parts of the description are used for other inputs, then the effects of read errors in those tuples will be quite uncorrelated because they never occur together, basically, because the input is either processed by one part of the machine or another part. So that's a sort of brief explanation for why these expectation values are sort of can be reasonably thought of as reflecting something about internal structure of the machine. Okay, and this is the proposed connection between computational structure in the Turing machine and the geometry via this Taylor series expansion of H and via H's kind of asymptotic relation to the KL divergence, which governs this, governs learning of this synthesis problem. Okay, I realize that's a lot, but please feel free to ask questions, even simple ones about what I just said. I want to get across like the kind of high level idea more than the details.
I have a question.
Yeah.
So from what I understand so far, it seems like each Turing machine gets a unique point in this space. Is that right?
That's right. Yeah.
So then the point itself contains all the information about the structure, right? We don't even need to look at the geometry around the point.
Yeah, that's right. So every point contains a complete description of the Turing machine. But it's a bit like, is the structure of DNA present in just the letters, or is it present in like the actual running of the DNA in the presence of like all the stuff that actually executes it, right? So arguably it's true that the information in the Turing machine is there in the description and therefore in the point. But in some sense, you have to supply what you mean by structure. So that's maybe one way of putting it, is that the embedding of the Turing machines into a continuous space is a choice. There isn't a canonical such thing. And any such choice implies a way of unpacking the information in the Turing machine and making it like sort of visible via the geometry. And so this Taylor series expansion is like giving you one answer to the question of what is inside that description. But it's, obviously the point itself contains everything there is to know. Yeah.
Maybe it's like it's easier to access from the geometry than from the original point or something.
Yeah, I think it's a bit analogous to various other situations where, like, if I give you a polynomial equation in 30 variables, some huge complicated equation, and then ask, does it have any solutions? So equals 0. and I ask, does it have any solutions? And then I say to you, that should be easy. Like it's all the information is right there on the page, right? Like that doesn't mean that it's accessible or that it's like it's all condensed, right? So to understand the structure, you need a way of like pulling it apart.
Okay.
Yeah, Paul.
Howdy. So I'm going to pretend that this is a naive question, but it's going to be phrased in some sort of pompous way. But here's the way I'm going to ask the question. I want to think about what you're describing as being a map from like intentional descriptions of a probabilistic program to extensional descriptions, in the sense of like you've got the intentional one, which talks about, like input tape and all of this business, and then the extensional one just being the table of how it acts. And I guess what I want to ask is there's going to be some like group invariance of this map. And are you saying that you can see that in the coefficients of the Taylor expansion? Is like that the kind of flavor I should be trying to read out of this?
Yeah, I think the answer is yes. I mean, by group, I think you just mean like ways of changing the.
Exactly. No, I'm just assuming that like there's deformation. There's some like system of deformations on the source, and we're identifying the geometry as correlated to that which it is invariant with respect to.
Yeah, that's the right way of thinking about it. Yeah. So we'll see some pictures in a moment, and I'll talk about ways in which you can change the noisy Turing machine without changing, while keeping it a solution. So without changing its input-output behavior. Yeah.
And then just as an aside, I like your comment with regards to DNA. This is something that Lewontin, the communist geneticist, was always a fan of. Whenever someone would say that the set, like DNA builds a cell, he would say it's bullshit. The cell reads DNA.
Yes. Matt.
I think Chris was first.
Oh, okay. Go ahead, Chris, then. I'm sorry if maybe hands up that I don't see, because I can only see part of the participant list. So someone tell me if I'm not mentioning someone. Go ahead, Chris.
So if we take in theorem 6.1, if k is just one index.
Yep.
So you kind of have hinted that there's more complexity to how we propagate uncertainty. But can I basically think about this as a kind of Markov decision process where my policy is given, I want to read a certain part of the description tape. Every time I do that, I draw an independent random sample given by this code, right?
Yeah, so the actual way to think about it is that each time step of simulating the machine, you're going to put a distribution on all the work tape squares and the state tape square. And you're going to update those individual distributions in every time step, such that sampling, so every time the UTM goes to look at any square, so the state squares or the work tape squares, it needs to sample from them. And those samples will be independent of all previous samples. And so that requires you to like if you want to look at what's under the head right now, you need to look at, well, what was under the head before, which determined what was under the head now, and take independent samples of those, and then independent samples of whatever led to that, and then independent samples of whatever led to that, all the way back to the very beginning of the execution where you're sampling from the original uncertainty on the description tape. So it's much more exotic than just like sampling from the description tape independently every time we look. Yeah.
Okay, so is there, would you say that there is a reasonable way to reinterpret this as like a Markov decision process where okay, well, not exactly that, but anyway, some situation, it's a random process, right? We can define it as,
you can think of this as a big graphical model that sort of is
graphical model, certainly.
Yeah.
Okay. All right. So when k equals 1, if I just want to know how does how does the output distribution change if I change one component of this probability distribution as defining the distributions over these states? This is kind of the policy gradient theorem ish, right? From reinforcement learning, like we would ask, I have this big graphical model, and I want to look at this outcome, and I'm changing some things which intervene at every step.
Mm-hmm.
And I have this kind of sum. Okay, so that's pretty cool. In machine learning, you very rarely take higher derivatives, but I sometimes wondered like,
yeah, that's true.
Yeah, but I guess the complexity here is like if all you have is this policy gradient theorem type thing, all you would say is, well, there are some things which don't matter and some things which do matter. But in some sense, and I have not really understood theorem 6.3 at all, but it feels like in some sense you're saying that, well, this thing doesn't matter, that making this one variation doesn't matter, and making this other variation doesn't matter. But if you do both of them at the same time, now that will have an observable effect.
Yeah, that's right. Yeah.
Okay, that's really cool. Because I think this is one of the questions I've had since encountering like the idea of singular learning theory. Like, yeah, cool singularities, but like, what do they look like for a program?
Right. Yeah. That was. I mean, a lot of the purpose of doing this was to actually have a case in which we could like really understand the answer to such a question. Yeah.
Okay.
I think I'll wait till the end to take further questions. So I think I just have one or two more slides. So you can see the paper for examples of how you can use this formula to sort of reason about degeneracy. Degeneracy here just means vanishing of derivatives. So if you think about it, like high degeneracy, meaning vanishing of many derivatives of h, means things on the right-hand side being zero, which might mean, for instance, that these random variables are often uncorrelated. So one way to have that happen is just to not have errors, right? So if reading from the description tape some number of times just can't change the output, and having errors occur just can't change the output, because, for example, maybe you're doing majority voting where you run the simulated machine runs itself 3 times and then takes a majority vote, then you'll always correct at least one error in the execution, as long as that error is not in the part that does the majority vote. So in that way, you can get vanishing of derivatives of h if you have error correction in the machine. I already sketched out how processing different sets of inputs differently might lead to vanishing of some of these correlation functions, and so on. So this is sort of now an open area to investigate. Like this theorem is, I mean, I don't want to suggest like this is difficult mathematics behind this. It's kind of like complicated and so on, but it's like this is not like a hard theorem. But once you have this language, it sort of gives you a way of maybe constructing examples of links between structure and degeneracy. I'm over time, so I think I have to very briefly, and I want to hand over to Billy with some pictures for maybe another 5 minutes or so. So maybe I'm just going to skip this, but there's a somewhat laborious calculation in the paper of an actual Hessian of detect A. There's 30 directions, 24 of them. 24 of them are 0 sort of columns in the Hessian, it turns out. And the remaining 6 you can see here. And so then you can see that there's a local expansion of H. And one of the directions, to come back to an earlier question that was asked, one of these directions with a large positive eigenvalue is actually this position in the description tape that seems like intuitively important. So that is the one where if you see an A and you are in state reject, you should switch to state accept. So errors in this position in the description, like the machine is very, very sensitive to those, which corresponds to this being a high curvature direction in the Hessian, which makes sense. Other directions, it's much less sensitive to errors because they're less important. And the like degree of sensitivity has got to do with the sort of degree of vanishing of H. Okay, so maybe I'll just set up for the pictures and then hand over to you, Billy, for a bit. So Billy wrote some code to actually compute all these quantities, thereby finding an error that Will and I had in the paper. So to plot some pictures, what we're going to do is take H, which is a function of, this is for detect A, so it's a function of 30 variables, these variations in the code that I introduced. But we'll fix all but 3 of them, Wi, Wj, Wk. And just because that's all Billy got up to like this morning, like as of this morning, we're going to truncate to degree 5, but you can go higher. You can do all of them. And then look at the set of solutions, and we're going to have some pictures. Okay, so this is one I've got in the slides here. This is 23, 24, 25. These are the indicated directions of varying the code. That gives you a 3-dimensional space of variations. That's this space here. So X is 23, Y is 24, Z is 25. And this point marked with a circle here is detect A. So the blue is the 0 set of H. And you can see that it's this singular point there. So this is not the whole singularity. This is 3 out of 30 directions, but this is like a visualizable slice of that geometry, and it appears. I mean, it's a bit unclear how degenerate it is, but it seems to be an AN singularity of some kind, for some n.